In the alkaline earths, you can use nuclear spin states in the ground electronic orbital, metastable nuclear spin states. You could do a ground to metastable qubit. There's also been a recent proposal of a excited fine structure qubit, because both the triplet P0 and the triplet P2 level have very long lifetimes. So you could do a terahertz frequency qubit between those two levels. This was just proposed by the group over in Stuttgart. So there's a lot of options and a lot of interesting work going on with those atoms. Okay, probably I don't need to dwell on this. People know how to do laser cooling. There's different techniques. Generally, qubit experiments with neutral atoms have not yet been done with atoms that are as cold as they could be. So they generally have not been cooled all the way to the ground state. And I think doing that is probably going to be important for reaching even higher fidelities than have been generated so far. And I'll just move on. Okay, atom trapping. So you could prepare arrays of trapped neutral atoms in different ways. Optical or magnetic traps are possible. Magnetic trap arrays tend to be close to surfaces, which is problematic. You get light scattering and you get fields from impurities or dipoles attached to the surfaces. So the optical approach is really much more developed. Magic trapping techniques, which were originally developed for atomic clocks, are very important for extending coherence. And magic traps can also be used to trap both the ground and these Rydberg states that are excited. And so let me take a few minutes and talk about magic trapping aspects of this field. When we talk about optical trapping, there's really two varieties to think about. There's red and blue traps. In the so-called red trap, we're using, say, a focused Gaussian laser beam, and we use a wavelength of that light such that the atoms are attracted to the regions of highest intensity. So that's the intensity profile of my laser beam. I get a trapping potential or a light shift that looks like this, and the atom will be trapped down here where the intensity is high. So that's great for moving atoms around, for rearrangement, as we'll see in a moment, and relatively straightforward way of making large arrays of many so-called tweezer traps. In some sense, it's not ideal because the atom's sitting at a location where there's lots of laser light. So any noise on the laser light gets transferred onto the atom and can degrade the coherence. The alternative is blue traps or blue bottle traps. Here we use a wavelength of light that repels the atoms. So you wouldn't think that's a trap. But if you make an optical bottle, which think of that as a dark spot surrounded by light in all directions, you can trap the atoms at a minimum of the intensity. So here's the cross section of a bottle. The red is the intensity, and then the green is the trapping potential. So the atom gets trapped at this local minimum. And this turns out to be really nice for trapping alkali Rydberg atoms. You can get reduced coherence, and there's also ways of making large arrays of these bottle traps. And I'll show you some examples of that. I should mention, if you're working with alkali atoms, you really need the blue traps for trapping the Rydberg states. If you're working with the alkaline earth type atoms, strontium or ytterbium, you can actually trap the Rydberg states either with the bottle traps or the red traps. They have more than one electron. They're divalent, have two electrons that interact strongly with the light, and that gives you some more degrees of freedom for engineering that trapping. But I'm not going to get into that. So people have made really nice arrays in many different groups. 1D, 2D, and 3D geometries are possible. Here's some work from the Roes group in Paris. Here's some work from Shannon Whitlock, also in France. And here's a really large uniform array. This is not atom trapping, but this is just the optical tweezers from the Lucan group. I think more than 1,000 spots of light. So clearly there's a potential here for scaling up. And I'll show you some pictures where we've trapped atoms in arrays of 1,200 spots now. So,
What's the scale of these?
Yeah, so the individual traps are typically separated by 5 microns. Could be a little bit less, a little more, but it's typical scale. So magic trapping, if we think about Rydberg atom computing, Generally, we need at least 3 states. We're going to need a couple states to encode a qubit and some Rydberg state to get strong interactions. And ideally, you want to trap atoms in all 3 of those states simultaneously in identical potential, such that when you transfer the atoms from down here to up there to implement logic operations, you don't excite them mechanically and cause heating and decoherence. And qubit coherence is in general limited in these systems by magnetic noise and by differential light shifts on the qubit and on qubit relative to Rydberg level. And they can be induced by laser intensity noise. And they're also dependent on the atom temperature, because an atom that's moving around, if I go back here, if the atom's moving around in one of these potentials, then it will over time see different intensities. And if that intensity affects the levels differently, you'll get a time varying shift of your energy states, which is not good. So, how does that work out? Optically, if I shine light on the system, say a red detuned trap laser, that means the frequency of the light is below the ground to first transition here. What happens is the qubit levels get closer because the let's see, the red detuned light shifts the levels down. And so this initial separation here that I've indicated by the hyperfine frequency actually gets reduced. The levels get closer. Well, what if I go to the blue side? If you go through the way the Stark shifts work and the detunings, they also get closer. So blue or red, in both cases, the levels get closer. They're not independent of that trapping light. Oops. So to make the qubit frequency independent of trap intensity, what you can do is add a laser tuned in between these ground state levels, and that will push the levels away. So a weak laser with a tuned in between the 2 levels relative to an excited state, combined with a blue or a red laser, can, if you balance the intensities out, you can get a situation where there's no intensity dependence or no motional dependence, and you get better coherence. And that was actually showed a long time ago, about 20 years ago, in Near Davidson's group, where they looked at the coherence of untrapped atoms. So this is some Rabi spectroscopy. Trapped atoms, it was washed out, and then they compensated the trap and they recovered the original coherence. So you can do that. In practice, it can be tough because the compensation laser may be a different wavelength than the trapping laser. It's hard to spatially mode match everything. But that's one approach. There's been other approaches developed. You can also cancel the magnetic shift. Here's some really nice work from Trey Porto's group, who's in the ArcUS Center, where they showed that you could cancel the differential light shift while simultaneously being insensitive to magnetic field noise. And that uses these 2 pairs of states in rubidium and uses, I believe it was elliptically polarized light, and taking advantage of some details in the atomic response, you can actually get a situation where no matter how deep you make the traps, you have essentially no change in the qubit frequency. So this gets deep into the details of atomic physics, but these are important capabilities for these systems. What about trapping Rydberg states? So we're going to be going from the ground state up to these Rydberg states for doing gates, and we don't want the atom to fly away while it's in the Rydberg state. We like to trap it. And again, let me try and, in the interest of time, not dwell on this too long, but here's a spherical cow model of a Rydberg atom, if you will. The simplest possible way of thinking about it is there's a positively charged nucleus and core electrons, and then relatively far away, I have my valence electron that's been excited to a Rydberg orbital and is far away. And the polarizability of an electron is negative. The electron is negatively charged, so when I shine light on an electron, its energy goes down. Okay. If I use a blue detuned trap, that's also locally reducing the energy of the atom. And so if I want to trap a Rydberg atom, in particular an alkali atom, I need a blue detuned trap to have the same sign of polarizability for the atom in the ground state and the atom in the Rydberg state. And I should choose the wavelength and the trap size so the ground Rydberg potentials are matched. As I mentioned, in divalent atoms, the alkaline earth atoms, the situation is different. The second valence electron can be used to trap the atom, while the first valence electron is Rydberg excited. So there's some different details there. This work from Derivianco group goes into those details. If we look at that a little more closely, we get curves like the following. So here I plotted versus wavelength the polarizability. And the polarizability multiplied by the local intensity tells you the energy shift of the atomic state. So this red curve here is the polarizability of a cesium atom in its ground state. And depending on the wavelength, there's some resonances. But in this region here, it's negative. And this blue curve is the polarizability of a free electron. And the Rydberg polarizability is essentially given by that free electron. And you see they have the same sign, but they don't have the same magnitude. For a broad range, the Rydberg polarizability is smaller in magnitude than the polarizability of the ground state. However, the Rydberg electron is delocalized. Here's a cross-section of, say, a bottle beam type trap. My ground state atom sits in the center. My Rydberg wave function is micron in size. And so the Rydberg electron sees regions of higher intensity at the edge of the trap. And so for a particular atomic Rydberg state with a particular spatial extent of the wave function and a particular size of the trap, you can arrange things such that the smaller polarizability multiplied by the higher intensity seen by that electron gives you an integrated light shift. What's going on here? Given by this formula, such that effectively you get the same light shift for the ground of the Rydberg state. So it's not a magic wavelength, but it's a magic trap that's been engineered to be magic. And here's some examples showing that you can actually do that. This is some work that, for reasons I cannot explain, we never published, but it's in a thesis from my group where we did this with cesium atoms and showed that we could get long lifetimes with essentially mechanical lifetimes of 350 microseconds, which are very long compared to the sort of 1 microsecond gate times. And we also showed that we could tune in parameters to get essentially a magic condition, no shift between the ground and the Rydberg. We will do some more work and publish this at some time. But more recently, there's also been demonstrations of this trapping of Rydberg states by the Broes group and also the Roche group in Paris, where they show here's an atom, Rydberg atom walking away is the red curve. And with this bottle beam trap on, they get a much longer lifetime, showing that they're trapping it. So you can actually do this. Okay. Going back to working with single atoms.
So, I mean, this fact that you can trap these Rydbergs in a way that's comparable to the ground state is very impressive, but is it really necessary? I mean, if you're only exciting the Rydberg, if you're only using the Rydberg state for a very short amount of time, wouldn't it be okay to just, I mean, is it really necessary for the goal?
Yeah, that's a great question. And it's not actually being used yet in gate and circuit experiments, because you are indeed exciting the Rydberg atom for a very short time. And so the atoms are cold, and even though you don't trap them, they don't walk away. So my perspective is that this is something we are going to need in the future once we make other things better. So the current state of the art in this field is that the gates are not super high fidelity. They're now 97% is sort of the best gates. And so you can't run extremely deep circuits because the infidelity builds up. But once we get the gates better and do want to run very deep circuits, then the small error you get from having a epsilon probability that the atom did walk away will build up. So we will want to do this in the future, but it's not been significant so far.
Okay, so let me move on to atom rearrangement. Here's a picture of single atoms loaded into a very large 35 by 35 site trap array, and the loading is stochastic. And in principle, you could work directly with a partially filled array like this. These Rydberg interactions are very strong and they're long range. So you could load stochastically, take a picture where the atoms are, and then tell your compiler to implement laser pulses and gates that just use the atoms where they are and do that. In practice, that turns out to be a lot of software work and so on that's not being done yet. And what has emerged as a much more powerful and convenient solution is to do atom rearrangement, to convert something like this into a completely filled subarray. And so you don't have to worry about where the atoms are. And this was demonstrated 5 years ago, pretty much simultaneously by 3 groups, one in Korea, the group at Harvard, and the Paris group. And so they all use, interestingly, different approaches. So the work in Korea, which was actually slightly first, they used a spatial light modulator to move traps around and then go from a disordered sample into an ordered samples with different structures. The Lucan group at Harvard started with a 1D array, although they're now doing 2D, where they had a line of tweezers. They took a picture, saw which tweezers were occupied, which were empty, and they just moved the occupied tweezers over to be next to each other or to create patterns in that way. And then the Broes group used a 2D acousto-optic deflector to move atoms around and create whatever spatial pattern they wanted. So this has now become really a standard tool in the kit of gold atom people, and you can do this in 1D, 2D, or 3D. This is sort of my favorite example where the Broes group did an Eiffel Tower with atoms, which is just really cool. Most people are using red traps. My group's mostly been using blue traps. And so here's just an example from Madison showing that you can also do this with blue traps. And here you can actually see the what the movable tweezer is doing to move atoms around on our monitor screen. So this has become pretty standard and works well. Oh, yeah, great question. Yeah, so when you load these arrays of traps, the traps are quite small. You can, in principle, get more than one atom. But what was shown by Philippe Granger first 20 years ago is that if you put more than one atom in one of these very small traps, collisions will eject the atoms. And so generally, the atoms get ejected in pairs. So they have hyperfine changing collisions that change the hyperfine state, release a lot of energy into the motional state, and they leave the trap. And so if you start with an even number of atoms in your trap and you have collisions, you'll end up with 0. If you start with an odd number of atoms and eject the atoms pairwise, you'll end up with 1. So on average, half the time you have an even number, half the time you have an odd number. So you get loading of single atoms with about 50% probability. And it turns out you can do better because you can arrange things such that the collisions don't eject atoms pairwise, but eject atoms one at a time. And then if you have at least one atom, you'll always end up with one atom. And that works up to about 95% level, actually, if you play some more tricks. So you just get one atom because the traps are small. In practice, for example, in my lab, we get mostly one atom. Our traps are not quite small enough. So sometimes we have 2 atoms in a trap. And then we turn on some extra light to enhance these light-assisted collisions, and we get rid of those 2 atom states.
So I wonder, are there any disadvantages of these blue traps compared to red traps? Well, in some cases, you can use those. Which one would you choose?
Yeah, so the optics of the red traps is simpler. They're a lot easier to work with. The optical systems that we use to make blue traps tend to be more complicated. I think longer term, they will be advantageous for the alkali atoms because of this Rydberg trapping, although it's not being critical yet. And so, you could use either, but what are the wavelengths you have available? How much power do you have available? There's other sort of system level considerations, but the highest gate fidelities have been done now, both in blue and red traps. Does that answer your question?
Oh, sorry, I'm not sure. So during this blue traps, you could get higher gates and higher fidelity.
I'm saying that people have demonstrated high fidelity in both blue and red traps. I think ultimately, when we get to very high fidelity, the blue traps will be preferred because of the Rydberg trapping. But this has not been important so far. Yeah, so if you're trapping your atoms in 3D and you want to control one inside the 3D array, well, the laser beams to do the control will go through other atoms and disturb them. And so remarkably, and this is really Dave Weiss who's pioneered this capability, you can then go back and correct those disturbances and still, with very low crosstalk, control the quantum state of an atom inside an array. It's not simple to do that. So, you could ask, should I work in 1D, 2D, or 3D? Higher dimension obviously has better connectivity. You have more nearest neighbors. My opinion is that 2D is a good compromise because you don't have the same crosstalk problem, so you still have pretty good connectivity. But Dave Weiss and also some work from the French group are looking at 3D. Okay, if we're really going to scale this up and build a big computer, we'd like to make very large single atom arrays without any defects. And we can certainly scale up the optics to thousands of atoms. The atom rearrangement may require multiple attempts, as when I move one of these atoms over to fill an empty site, it doesn't necessarily work perfectly, and I might have to take another picture and try again to get all the sites filled up. And so to really scale up to very large arrays, we are going to need long vacuum lifetimes, so we don't lose the atoms due to collisions with untrapped background molecules. And we also need the ability to measure the presence of an atom without loss. Those are both requirements for preparing large arrays. And so, what's the current state of the art? So here's some work on the archive from the Broes group. And they've done two things here. One, they're working in a cryostat. So this is not a dilution fridge, but it's a 4 Kelvin cryostat. And in the Rydberg field, this has two benefits. One, you get really good vacuum lifetime. So typical vacuum lifetimes for trapped neutral atoms are, say, tens of seconds in these kinds of experiments. By going to a 4 Kelvin cryostat and getting cryopumping, they achieve vacuum lifetimes of 6,000 seconds. They got way better vacuum. Plus, it turns out the gates will be a little bit better fidelity because the lifetime of the Rydberg states that I mentioned scaling as n cubed, there's a prefactor, and that prefactor actually gets a bit larger when you go cold because there's less black body, which depopulates the Rydberg state. So you actually can get also a little bit better gate fidelity. In any case, they worked in a cryostat and they went to a lot of trouble to make the intensities of their trapping sites very uniform so that all the sites trap equally well. And what they showed, and this is really the current state of the art, is that they could assemble a 324 site array with 0 defects 37% of the time. So that means if you try a few times with high probability, you can actually prepare an array that large with no defects. That's sort of the current state of the art. And, I think we'll see this go up into the thousands in the next couple of years, but we're not quite there yet. And so one is to have the good vacuum, to have very long lifetime. The other is to have good measurements so we don't lose the atom when we're checking if it's present. So let me speak a bit about the measurements. Different techniques are possible. Most widely used method of imaging single atoms is just looking at the light scattering or resonance fluorescence.
In the attempt on trying to put the atom in 3D,
like I think there are some files to make it on 3D. Is it on optical trapping or optical ladder?
So the work in Paris is actually tweezers. The work that Dave Weiss is doing are large period optical lattices.
Like for tweezers, they have like it is X hypertrophic as XY, but the Z is easy access to the different. So there's no an isotropic. Yeah.
Yeah, so how are they doing it in 3D? So they have some axial focusing planes. I have to admit, I don't remember all of the details of exactly how they did that Eiffel Tower, but they're generating a 3D pattern of trapping sites, and they're using a tweezer that can move both in XY but also in Z to fill those different sites. But it's a true 3D pattern.
Is it like back and are what is it happening? And you have to figure out, the image and figure out when to move.
Sure. I mean, that's a great question. There's a lot of technical details around it. So single moves of the atoms, you have to grab an atom, move it, and then deposit it where you want it to go. They typically take a few milliseconds, but you can move more than one atom at a time by sending different frequencies into your acousto-optic deflectors. And then, there's a question of what's the best algorithm. If I start with something like this, and then I want to create a particular filled pattern, which atom should I move in what order? And there's been a lot of recent work on different algorithms and different ways of optimizing this. We could spend a whole hour talking about that, but that's certainly an area of active work. And if you look at papers from Rowe's group and others, you'll find lots of information about developments in that area. But it takes some time to fill a array of hundreds of atoms. Will take some tens of milliseconds. Okay. Yeah, measurement. So generally, there's a trade-off between the fidelity of the measurement. Do I have an atom or don't I? And the probability of losing the atom while I'm looking at it. And the longer you look at the atom to get a more accurate measurement, you tend to heat the atom by shining light on it to look at it, and that gives you loss. And so here's a nice example of that. Some very recent work from the Kaufman group using ytterbium, actually. So here's their ytterbium array, a 10 by 10 array of ytterbium. And here's a plot for a relatively long measurement, 120 millisecond duration measurement. They varied the intensity of the measuring beam. And if they went to high intensity, they got a high loss probability, but a very low infidelity. So when the atom was not lost, they were very sure it was there, but there was a high probability that they lost it. If they went to low intensity, they never lost the atom, but they weren't sure if it was there or not. So it's sort of, you can't win here, but there's sort of a sweet spot in the middle where you have relatively low loss and relatively low infidelity at the level of 1% or so.
How do you tell if you lost it versus if you measure it?
You make a second measurement. You make another measurement in the regime where, yeah, right. So, what's the state of the art in terms of making low loss measurements? I think the best results are actually with strontium from the Endres group at Caltech, where they're using a couple colors of light at the same time. So in these alkaline earth atoms like strontium, you have this very strong cooling line in the blue. And so that scatters a lot of photons rapidly, which is good, but you tend to get heating. And so they're looking at these scattered blue photons for the measurement and then simultaneously cooling on this narrow intercombination transition that keeps the atoms cold, even though they're scattering a lot of photons. And that worked very well. They could measure an atom and have only 10 to the -4 probability of a loss. So the retention is better than 3 nines. And the fidelity of knowing whether or not an atom was there was about 4 nines. So they could image a single atom 2,000 times repeatedly without losing it. And they also, so that just shows you if you have an atom or not. For error correction, you're going to want to know what state you're in, or even just for reading out the result of your quantum circuit, you want to know what state you're in. And then this is more complicated, but they had a way of looking at, this was an optically encoded qubit using the ground state and the, sorry, not an optically encoded qubit, but they used one of the metastable states as part of the measurement protocol here and could selectively excite to those metastable states to get a state measurement, not as good as just the occupation measurement, but about 2 nines, both for the retention, better than 2 nines for the retention, and about 98% fidelity. This is about a 15 millisecond duration measurement. If we think about the alkali atoms, where we're trying to measure a hyperfine qubit, generally what we do is we cycle from F equals 4 in cesium up to F prime equals 5, and then selection rules just let us cycle back and forth. We collect photons, so we can get very well separated histograms with really zero overlap between the 0 and 1 quantum states. However, one suffers from Raman transitions, and that there'll be some off resonance scattering from this other level, which can decay down to the lower state, so you don't know what state you're in. This issue can be solved by pumping the atom into a stretch state. That is, if I work from this state here and use sigma polarized light, then I don't suffer Raman. If I have good polarization, I just cycle back and forth up to this state here, and there's no 4,5 state, so I don't have any Raman transitions. And that's been done. And here's an example of that in a cesium array. Here we're measuring in about 4 milliseconds, and we do, these plots show 2 measurements. We do a first measurement with a very long exposure that is not state selective, but shows whether or not we have an atom. And then we do a much shorter measurement, scattering or detecting about 20 photoelectrons, and we still get well-resolved histograms. And this works at sort of the 97% or so. So these are state resolved measurements relatively rapidly. And there's also other approaches. Dave Weiss has used the Stern-Gerlach method. So the type of lattice that they're using in 3D allows them to implement spatial motion of the atoms depending on their quantum state by varying the polarization of the lattice beams. So what they can do is separate the atoms spatially depending on their quantum state and then just measure the occupation. And doing that, they were able to get measurement fidelities of 3 nines. And very recently also from Dan Stamper-Kern's group, there's been a nice demonstration of cavity-assisted readout, where they're using this ability to move atoms around, not just for rearrangement, but for the measurement. So you can think of having an array over here, moving the atom you want to measure into an optical cavity and using the feedback from the cavity to make a faster measurement. Here they're measuring in about 100 microseconds, much faster, with a fidelity of about 99% or so. So that's another approach. Ultimately, one wants to make the measurements a lot faster. If you think about a future error-corrected quantum computer, that error-corrected quantum computer is mostly just going to be making measurements for error correction. And so the gates are microsecond time scale, but if the measurements are millisecond time scale, that's 1,000 times slower. So we'd like to get the measurements faster. And there's been some ideas and also results in terms of doing that. We proposed a long time ago to map single atom qubits onto multi-atom ensemble qubits and use the fact that if you have more than one atom, you can scatter photons more rapidly and make a faster measurement. A kind of related but simpler idea was demonstrated by Vladimir Gulatich's group last year, where they're using Rydberg-controlled electromagnetically induced transparency, and we're able to read out quantum states in 6 microseconds. Not yet with super high fidelity, although Vladimir tells me they think they can really improve on this significantly in the near future. So, the Rydberg interactions can be used not just for entanglement, but also to enable faster measurements, which is really quite interesting. Okay, so that's measurements. I can see I'm going way too slow. Let me not dwell on initialization, which relies on optical pumping, and now move on to some of the Rydberg specific things and talk about excitation. And I have a lot of slides here. I think I'll skip some of them, but and show you some. But how do you actually generate these Rydberg excited states? And you could use 1 photon, 2 photon, or 3 photon to get up to low angular momentum states. If you want to go up to these circular states that have these very long lifetime scalings into the 5th, you need to invoke some special techniques. I'm not going to talk about that. In general, for quantum information, we want the excitation to be fast, coherent, and state selective. And using laser systems, you can now go out and buy. That's relatively straightforward. So you could do a 1 photon excitation that'll take you from an S alkali ground state to a P state. You could do a 2 photon that'll take you up to an S or a D state, or you could do a 3 photon even that will take you up to P or F states. You'd like to be able to calculate the rates if you're working on this. Let me skip over that. There's sort of fairly standard expressions for Rabi frequencies. If you go through the angular momentum algebra, this really boils down to calculating matrix elements between ground and Rydberg wave functions. There's lots of ways of doing that, of calculating these overlap matrix elements between the ground wave function and the Rydberg wave function. You can use WKB approximations, Coulomb wave functions, model potentials. These days, there are online calculators that will do that for you. One interesting point, perhaps, is that if you look at the matrix element calculation, you have the product of the radial wave functions of the ground state and the Rydberg state. So here's the wave function of a ground state cesium atom, and here's the wave function of a 50p Rydberg state, which is much more extended. If you look at the contributions to the integrand, it's all localized near the core. Everything is happening actually at the core, even though the wave function's extended. And that's because a free electron cannot absorb a photon. This Rydberg electron way out there, away from the nucleus, is approximately a free electron. It's not a free electron, it's bound, but it's sort of acts like a free electron. And so the actual transition is occurring in the core, not out of the edge, because that's where all that amplitude is in the integrand. Let me skip that. Apart from saying that the matrix elements decrease as you go to higher and higher Rydberg levels, so you need more and more intensity to do that excitation fast. You can, let's see, maybe I had it somewhere else, sorry. I just want to say that this integral scales as 1 over n to the 3/2. So as you go higher in principal quantum number, you go slower because of that factor. And that's just to do with the overlap near the core of the wave functions. Okay, so you can do a 1 photon for an alkali atom that's generally in the ultraviolet, around 300 nanometers. It's not so commonly done. Also, you have a lot of Doppler sensitivity if you just use a 1 photon technique. Here's some old data from Hench group showing that they could do this in rubidium atoms. Most commonly, people use 2 photons, where you're detuned from an intermediate state. That gives you some scattering from that intermediate state. But if you have a lot of laser power available and detune very far, you can reduce that scattering. And in fact, you can relate the probability of a spontaneous emission from that state to your ground Rydberg 2 photon Rabi frequency and the intensity of the excitation lasers, as well as the lifetime of that intermediate state. So skip that. It can be better to use not the first available excited state as a path up, but the second state. So you could go with the first photon in the red and the second one in the blue. through the first excited state in rubidium. This would be the 5p, or you could do a first photon that's blue going through the 6p, then a second photon that's in infrared. Turns out this second technique has become the favored approach for two reasons. This second excited state has a longer lifetime than the first one, so you get less intermediate state scattering. And then the matrix element from this slightly higher energy state with the Rydberg state is stronger. And so it actually works out to your advantage. Supposing you want to excite at a certain Rabi rate, you have a certain amount of power available. If I want to keep the intermediate state scattering, which gives you an error at the 10⁻⁴ level, you're not going to be able to go very fast through the first state with a finite amount of power. If I use the second state, I can go much faster for the same amount of power and the same scattering rate. So you do much better there. Okay. And then you have less Doppler than if you had a one photon, but you still have some Doppler broadening. And if you counter propagate those two beams, you can substantially reduce the Doppler broadening by about a factor of 4, say in rubidium. And here, I'll just show you a plot here. Skip that. Sorry, too much stuff. You can also use 3 photons. 3 photons is cool because if you choose a particular geometry, depending on the wavelengths that you're using, there's a coplanar solution that is Doppler free. So you can get from the ground to the Rydberg state without any Doppler sensitivity. This was proposed by the group in Novosibirsk some years ago. And so here's a comparison. So here's for different temperatures of the atoms. So 0 Kelvin is a motionless atom, 1 microkelvin, 10 microkelvin, 100 microkelvin, millikelvin, up to room temperature. Here's 1 photon, 2 photon, and 3 photon. If you're not moving, then you don't have any Doppler broadening. As you get hotter, then the 1 photon excitation starts to fail, 2 photon does better, and with 3 photons, you can even be at room temperature and have substantial Rydberg excitation. Most people are using 2 photon excitation. Okay. There's an example of it. I'm going to skip that. And maybe just end this part with some look at what's been done with coherent oscillations. So first Rydberg excitation experiments were back in the 70s, really not coherent, but spectroscopy. You could see these different Rydberg levels as shown here. This is from 1973, relatively low resolution. Here's some work from MIT, from the Kleppner group from the late 70s, with these very detailed maps of the Rydberg energy levels in different electric fields, Stark maps. This is now about 10 gigahertz resolution. Here's some work from Reithel group from Michigan, early 2000s, showing using the Adler-Towns effect to actually quantify the rates of excitation up to, this was 44D Rydberg level. And we started to see coherent excitation in the many-body regime. There's 2008 from Matthias Weidemüller's group. And this is with about 100 atoms. And you see some signatures of oscillation, but it's not very coherent. And this is partly Doppler, but partly because you have a distribution of atoms and you have Gaussian laser beams. So different atoms are seeing different intensity and therefore different Rabi rates. And so it just washes out. So that's not very good. They showed they were able to improve on this by structuring the beam to have a more uniform spatial profile. You get better coherence. You can also just go very fast. So here's some work from Tillman Fowles' group where they did Rabi flopping at gigahertz rates using pulse lasers, and not super coherent, but they saw some oscillations in the Rydberg excitation. Here's the first single atom ground Rydberg oscillation data. This is work we did with rubidium, 2008, where you see this really coherent ground Rydberg transfer. This is a couple of years later where we'd improve things. There's been a lot of studies of, well, how do you get these oscillations perfect? And you need to really perfectly transfer from the ground state, which is the one here, up to the Rydberg state and back if you're going to do Rydberg gates. So there's been a lot of studies of different decoherence mechanisms, dependence on laser noise, etc. This is a paper from the Broa's group looking at some of those issues and comparing experiment with calculation. Really nice work from the Lukin group from 2019, showing here high coherence, high fidelity ground Rydberg oscillations, and showing that you could do this on multiple atoms in parallel simultaneously. So this is this 2-photon excitation through the, I forget which state they went through. I think this was also through the second level, even though the first photon is shown in red here, then a second photon, and showing really coherent ground to Rydberg oscillations. One of the things that's become apparent in recent years is that to make this work at the kind of fidelity level one needs for quantum dates, you need really good lasers. You need to filter the lasers and get rid of any excess intensity noise, any excess phase noise. And that's part of what was done in this experiment, is that they did some additional filtering on the lasers beyond what others had been doing. This is a typical setup for these kinds of 2-photon excitation experiments, where you have a very high finesse reference cavity that you're locking the lasers to, and then using those locked lasers for the excitation. I'll just skip that. So those experiments use constant pulses. And then let me just take the remaining 5 minutes before the break and talk a bit about adiabatic pulses. Supposing I want to excite out of an ensemble of atoms up to the Rydberg state, okay? So I have a number of atoms in the ground state, I have a Rabi frequency, omega, and a Rydberg state, R. If I do that in an ensemble, and the ensemble is blockaded, so I haven't talked about Rydberg blockade yet this morning, but let's assume that the atoms are strongly interacting, so only one at a time can be Rydberg excited. Then what happens is I create a superposition of any one of the n atoms being Rydberg excited. And so the state I create is a superposition of one of those n atoms being excited. And the coupling rate that takes me from the ground state to this symmetric singly excited state is root n larger than the rate for one atom, if I only had one atom, because I have n different target states, and if I properly normalize that, I get a root n enhancement. So there's this collective enhancement of the light atom interaction, which can be very significant, of course, if n is large. And this also allows for strong interactions at the single photon level. So there's work I won't talk about looking at implementing gates between single photons using ensembles of Rydberg atoms, which is really relying on this physics here with this root n enhancement. However, what this also means is that if I don't know exactly how many atoms I have, I'm not going to know what the effective Rabi rate is, and so I'll have a hard time controlling things. And so here you see an example of this root n scaling, where we're increasing the number of atoms from 1 up to about 15. You see that the frequency gets faster, but it also washes out because of those effects. So what can you do about that? Well, you could use adiabatic techniques. So one of the well-known methods for doing adiabatic state transfer is called STIRAP. And this uses this counterintuitive pulse sequence. So I have a 2-photon excitation from the ground state up to my Rydberg state, and I turn on the second photon before I turn on the first photon. So if there was no temporal overlap between those photons, I'd never get excited. But if you do it in this way and make the pulses adiabatic, you get a transfer from ground to the Rydberg state without ever populating the intermediate state. So you don't have any spontaneous emission. And it turns out the area of that pulse becomes independent of the Rabi frequency. So this root n factor here is no longer an issue. Okay, so it's kind of magic, but you can go from this ground state to the Rydberg state with an unknown Rabi frequency and always get a pi pulse, which is what you want for a gate. And this was done by the Rifle group in ensembles a long time ago. And you can also do it with single atoms. This is some work from my group showing that we could get very good excitation with a single atom and then back to the ground state using a stirrup type sequence. So there's some surprises though. These adiabatic pulses have a lot of rich physics involved in them. If the Rydberg atoms were non-interacting, 100% transfer from the ground state to the Rydberg state is theoretically possible. When the atoms are interacting, that is, I have a Rydberg blockaded sample, which only allows one at a time to be excited, stirrup will transfer 0 or 1 atoms depending on whether n is even or odd, which is not obvious why that works, and I'm not going to pause to go into the details, but this was discovered by Klaus Mulmer and his group also a long time ago. So that's very interesting. That gives you the capability of measuring the parity of n, which is in general something you often want to do for quantum information. So again, if you have a Rydberg interacting atoms and you do that counterintuitive stirrup sequence, you'll either transfer an atom to the Rydberg state or you won't, depending on the parity of the number of atoms. Kind of surprising, but that's the way it works. That's nice for parity measurements, but it also implies stirrup does not in general work to excite a single atom independent event, because half the time I'll have an odd number and I won't get an atom excited. However, so this is what I just said, worked out by Mulmer. However, the Novosibirsk people showed, well, if I just make a simple change and instead of doing the stirrup sequence where I'm resonant with the intermediate state, if I detune from the intermediate state, this parity sensitive physics goes away. And you get normal behavior. So you can transfer a single atom independent event. Again, I'm just trying to give you a flavor here. It would take too long to go into the details of why this exactly is, but these are the papers that explain it. And so if you detune from that state, you can excite a single atom independent event. And so that's cool because you can make the pulse area independent of the number of atoms in the ensemble. And then you can really think about doing quantum gates with ensemble qubits without having to know how many atoms you have in the ensemble. And you still, turns out you have a phase sensitivity on the wave function. So here's an example of doing stirrup transfers to the Rydberg state and back for different numbers of atoms, where I'm plotting the phase of the wave function, and it varies with the number of atoms. So that's not so good again for quantum gates, but then it turns out you can design stirrup pulses and also adiabatic rapid transfer pulses where you change signs of detunings in ways that get rid of that phase sensitivity. So you again become independent of n, even as you vary the number of atoms. So here's some plots with stirrup and with ARP, where I'm plotting the phase of the wave function for 1, 2, and 7 atoms. You see it's independent of the number of atoms. So you can actually solve these issues. Okay. We're out of time. It's coffee break. And I didn't get to the most interesting part here, which is Rydberg interactions. I'll fold that into part 2 after the break and then continue with gates and circuits and so on. Thanks.